Hello everyone, welcome to lecture 16. In this lecture, we're going to talk about the electromagnetic properties. The content covers the magnetic permeability and conductivity and polarization. We talked about in the previous chapter three main parameters, relative magnetic permeability and relative permittivity. So if it's just permittivity, it's epsilon, and the relative permittivity, then it's kappa. And we'll also talk about the DC and AC electric conductivity. So first section is about the magnetic permeability. Moving charge generates a magnetic field and magnetization of the material. So that this tells the how much magnetization occurs within a medium is proportional to the magnetic field intensity H. And here the psi is called the magnetic susceptibility. And magnetic induction B is sum of the magnetization and the magnetic field intensity. So then mu naught times H plus M, and here if you replace the M with the psi times H, and you get this equation. And the relative or the magnetic permeability of medium or of a certain material is mu naught times 1 plus psi M. So then how this magnetization occurs? Partial filling of the electron shells resulting in unpaired electron spins causes the magnetization. And depending on the material and how they react to the magnetic field, the materials can be categorized into three. So diamagnetism, or diamagnetic material, and paramagnetic material, and ferromagnetic material. And the magnetic properties of the material is affected by these three effects, three components: interactions between magnetic fields within the atom, and that magnetic field with neighboring atoms, and tendency for magnetic dipoles to become aligned in response to an external magnetic field, and the disorganizing effect of the thermal agitation. So this is about the effect of temperature and the diffusion. So this table shows the typical magnetic susceptibility of the material. So if you remember, magnetic permeability is mu naught times 1 plus susceptibility. And when it's paramagnetic, so then it becomes like magnet very easily. Then you can see that the psi is really high, like 10 to the negative 10 to the 3 to 10 to the 5. And diamagnetic and the paramagnetic, diamagnetic has the negative value. So psi is less than 1, less than 0. So the mu is negative value, less than 1. And if you look at the amplitude, it's 10 to the negative 6. So it's a really small value. And paramagnetic also is positive value, but the magnitude is very small. But it's so in terms of the relative magnetic permeability is very close to 1. So then what caused the diamagnetism and paramagnetism and ferromagnetism? The total magnetic moment of like a molecule is sum of the spin and orbital of moment. And here the diamagnetism is affected by or determined by the orbit of the electrons. So orbit of electron is modified to oppose the change when a material is placed in a magnetic field. The medium feels repulsion from the magnetic source. This dipole moment creates a small negative susceptibility. So when there's an external magnetic field like this, then the material, because of the orbit of the electrons, it acts against the magnetic field. So it feels the repellent. It means that this material is magnetized into this direction. Here is the N, and this will be the S pole. So that because of the repulsion, in terms of the magnetic induction the vector, it will be the opposite to the external field. The M will be opposite to the B naught here. So the psi value will be negative, and it's this kind of a diamagnetism is prevails in most material, water, copper, kaolinite. And paramagnetism is at a smaller scale. It's about the spin of the electron. So spinning of unpaired electron is causes the paramagnetism. And momeronite, granite, aluminum, magnesium is paramagnetic material. In the absence of the external field, some agitation ensures the dipoles are randomly oriented, so that in that case the magnetization is zero, net magnetization. But when external field induces the magnetic dipoles to be oriented parallel to the field, and it will, in terms of the force, it's going to be the attraction. So magnetization direction, it will be parallel to the external magnetic field. So here will be the N and this will be the S. But still the number is very small. So the attraction will be very small. But ferromagnetic material, the atomic magnetic dipoles are closely aligned, providing a strong magnetic field. So unpaired electrons are closely aligned in, like, for example, if it's the ion in some domain, and unpaired electrons cause the magnetic dipoles, and they are aligned, then providing a strong magnetic field. And this alignment remains until the Curie temperature, and exceeding this temperature, if this is the ion, then they become the paramagnetic. So it loses its magnetic characteristic. And permanent dipole moments form domain where the magnetic dipoles are aligned in the same direction. If in the case unmagnetized state, the domain direction renders the mediums with zero net magnetization. So in this case, the magnetization will be zero. But when the external magnetic field is applied, then the rotation of the spin within the domain or movement of the domain or occurs, and the material becomes magnetized. So then this magnetization is frequency dependent. So at high frequency, domain was unable to follow the field. The only magnetization mechanism is spin rotation in domain. At low frequency, the movement of the domain wall in ferromagnetic material manifests at a low frequency relaxation. So when we think about the relaxation versus resonance, resonance is like you have a spring and you get the restitution force very high, and the inertial effect is dominant. And relaxation mechanism is a damping effect is dominant and no restitution. So we'll see the difference soon. So then in ferromagnetic, and high frequency resonance develops by the electron spin, and it shows the real value, it will be like this, and the imaginary magnetic permeability will respond like this. In the low frequency relaxation regime, the real mu naught decreases with the increase in frequency, and the imaginary value will show a bell-shaped curve like this at about like 10 kilohertz. So then this, now that before this was for the single component material, like the pure material, and when you have like layers with different material, then magnetization will occur with some characteristic involving the A characteristic and the B characteristic, and it's called the mixture theory. So please review the mixture model. and this will also be applicable for the electric conduction and the polarization. So the second is the electric conductivity. So electric conductivity is measure of the charge mobility in response to an electric field. So the J times sigma times E is the Ohm's law, ohmic law. And when the medium is conductive, the medium is conductive when electrons can be easily removed from the outer valence shell of the atoms. These electrons are randomly moving within the medium, preserving the time average electron neutrality. So I think you've heard of the free electrons in metal or some materials, right? So if the in the orbit, in the most outer orbit, the electrons are freely removable, then it's electrically conductive material. The metal is the one good example of that. If charges are not free to move, the medium is dielectric or an insulator. So like silicon or some plastic, there is no free charge, free electrons, so it's dielectric material. Still, positive and negative charges displaced locally relative to each other in the presence of electric field, rendering a polarized medium and the polarization current. So this is related to the polarizability or polarization. In aqueous electrolyte, so let's say that you have a sodium like chloride solution, right? Maybe like 0.1 mole. Then you have sodium ion and the chloride ion in the water. And this sodium and chloride, or here that I drawn the potassium ion, then potassium ion will be hydrated with water, so it's surrounded by the water molecule, and also the chloride will be hydrated with the water molecule. And this hydrated ion will move as one cluster. So this will move when the electric field is applied like here. So you have potassium and water, water, water like this. Then the hydraulic radius of this medium or of this cluster will be bigger than the potassium ions radius. So R single ions. And ion mobility is terminal velocity per unit electric field. So the velocity of the ion divided by the electric field. And the ion's velocity is z times e over 6 pi the viscosity nu times the RH. RH is the hydraulic diameter and the radius of ions, hydrated ions. And this is a combination from the Stokes law. So in the bottom, it's from the Stokes law. So if we look at closely to the electric conductivity of electrolyte, so this is like what's the electric conductivity of like 0.5 mole of the potassium ion. Then it's number of hydrated ion times ionic mobility of each ion times the valence. So if it's like potassium chloride, then the valence will be 1. And as the concentration increases, that the U will have more hydrated ion. So the electric conductivity will be proportional to the number of ions, so that the concentration, and also the ion mobility, so that like potassium with water molecule this ion cluster, how much is the ion mobility of this ion cluster? So this will determine the ion mobility. So then, how do we determine the ion mobility? So before, the U, the ion mobility is defined as this equation. And let's derive it together. When the charge, for one ion, right, charge is placed in an electric field, then the force that the ion is feeling is Q times E. So Q is the charge and the E is the electric field that the ion is placed. And here the Q is the electron times the balance. So this is the force that's moving the ions, and there will be some drag force if it's moving inside the water. So the dragging force is this derived from, can be calculated using the Stokes law. So 3 pi velocity of ion times d, the diameter, and the viscosity of the fluid. And if you convert this one to the diameter to the radius, then the 6 pi v times r times mu. So then when it's terminal velocity, it means that the velocity is constant, so that the force is now in equilibrium. So then you can equate these two forces, and this will give you the ion mobility. So the molar conductivity of the electrolyte is the sum of the molar conductivities of the individual ions. So this shows the summation rule, superposition rule. And if it's monoionic electrolyte, so it doesn't have, like, this is the case when you have like sodium and maybe like something like this, right? If the electrolyte contains the different kinds of the ions, then you use this equation. But if it's just the only one kind, then this equation can be simplified like this. And this equation is valid for low concentration electrolyte. So as long as the ion to ion interactions are negligible, you can use this equation and you can use the superposition rule. But as the ionic concentration increases, then the ions will interact each other, because now they are come close. The distance between the ions gets very close. So the mobility of the ions decreases. At high concentration, the decrease in mobility may prevail over the increase in the ion availability. The conductivity of the electrolyte may decrease. So we may think that people think as the concentration, for example, potassium chloride, concentration increases, the sigma electrolyte increases linearly, but at some point it will be flattened like this, so the increment will be will decrease. So then it can decrease like this, because then now the ions are like crushing and each other, bombarding each other, so the mobility decrease, overall mobility decreases. In now that let's think about the soil. So low specific surface soil is like sand and gravel and silt. So in the case, the particle have its own electric conductivity, and there will be surrounding fluid, which is electrolyte, and it will have its own conductivity. So then, if, for example, if this is the soil with a lot of solid grain inside, and this is the particle, and this is filled with water, then what's the electric field, electric conductivity of this medium? So if we know the sigma p, and particle electric conductivity, and the electrolyte electric conductivity and porosity. Can we estimate the mixture conductivity? So mixture conductivity depends on the orientation of the layers with respect to the direction of the applied field. So we can think that this is the direction of the E, and we can have like two extreme model. One is the series model and the parallel model, like we practiced with the spring models. So the materials are aligned in series and materials are aligned in parallel, and you'll be able to derive these equations. And for the high specific surface mineral or high specific surface soil like clays, it develops the double layer, diffuse double layer due to the cation and the negatively charged surface. Clay particle is negatively charged, so that when the water is added, then this water gets absorbed on the clay surfaces, and it will have some kind of a stone layer where the water is like strongly bounded. And as you go further away from the surface, the water can move freely relatively with respect to its distance. And the cation also will compensate the negatively charged surface. So you have cations like this. And this cation can be hydrated or not hydrated. So it could be just absorbed on the stone layer. So cation concentration decreases exponentially with the distance. And with that, it develops some kind of absorbed water layer. It's called a diffuse double layer. Adsorbed water layer. And the thickness of the water layer is also an important factor in the clay science. So if it's a dry clay, you have some cations absorbed on the clay surfaces to balance the negatively charged clay surfaces. But as soon as you're adding the water, it will form a stone layer and the diffuse double layer, and it's just a free field where the water is and the cations are freely movable. So from this kind of image in the mind, to bear in the mind, and let's have some thought process for the dry soil and you're adding pure water. So in the dry soil, the dry clay, you have a cations balancing the negatively charged clay surfaces here. And there will be some excess salt just precipitated. And when you add the pure water, that means that I'm adding deionized water. There's no additional ions. Then this water will hydrate the cations, and it will form the kind of absorbed water layer called the diffuse double layer. And also the excess salt will be hydrated. So then by adding this in here, if it's dry, the conductivity is 0. So it doesn't conduct any electricity. But as soon as you're adding pure water, it will create the freely movable ions, and it can carry the electrons so that the electric conductivity becomes greater than 0. But as the porosity decreases, then the amount of the electrolyte decreases so that the electric conductivity decreases. But dry soil with no excess salt. What if there's no excess salt? So before there was excess salt like this, and now there's no excess salt. So then when you add the water, it will just like form some diffuse double layer, and this will be hydrate. Yes. And this charge is not movable. It's not freely moving and carrying the electrons. So then it will form only the double diffuse layer. So then when the electric field is applied like this, then if it's just one particle floating in water, then this diffuse double layer will deform. So the cation will be attracted to here. But because it has to keep the electron neutrality, because the surface is negatively charged, it cannot move away. And so then this kind of a local polarization will contribute the electric conductivity to a certain amount when it's AC, especially. But if the particles are very close to each other, so now that you have a lot of particles and they're almost touching, then this double layer can overlap. So then when there's electric field like this, then the localized or the polarized this double layer can overlap so that this cation can hop to the other particle. And this is called a surface conduction through diffuse double layer. So through the diffuse double layer, this diffuse double layer gets polarized so that the proton or the cations, hydrated cation can hop to the other particle, and that can contribute the conductivity. So in this case, because as you getting more particles, so that the particle to particle distances gets closer, the contribution of the surface conduction gets bigger. Right? So it will play a more role in the electric conduction. So as the porosity decreases, the particle will becomes closer, so they are more packed, so then the electrical conductivity increases. This is the case with kaolinite, with DI water at low porosity. So very highly compacted kaolinite with pure water can have this kind of a very significant surface conduction. So in high specific surface soil, like clay, the mobility of the ions in stone layer is limited by electrical potential wells associated with the surface charge. The ions in stone layer contribute to surface conduction only at high frequency. So I have the pictures, not in here, huh? And I will show you later. The ion mobility in diffuse double layer is the same as in the bulk electrolyte. The ions in the counter ion clouds near particle surface contribute to surface conduction. So it's like ions, the hydrated ions, cations are hopping to carry the electrons and contribute to conduction. Fine-grained soils with high specific surface may show significant conductivity even if the saturating fluid is deionized water without excess salt. The surface conduction is estimated assuming that ions in the stone layer do not contribute to the low frequency conduction. So in here, the low frequency conduction is like less than about like 10 kilohertz. Furthermore, because the ions in the stone layer partially neutralize the surface charges on the surface, zeta potential is used to determine the uncompensated charge density at the slip surface. So if you look at this figure, this is surface potential, and surface potential is proportional to the zeta potential. And further away from the stone layer, the zeta potential captures the surface potential, and this zeta potential is proportional to the how much charge is on a unit area of the surface. And this is the shear plane or slip plane. And zeta potential can be used to estimate the surface conduction. So zeta potential is proportional to surface charge density, and here surface charge density is expressed as this. So epsilon kappa and the permittivity of the water divided by the double layer thickness is surface charge density. So, so with that surface conduction, can we estimate the mixture conductivity? So before, in low conductivity on a low species surface material, the surface conduction was 0. And the sigma p, also the surface particle electric conductivity is also 0. But in this case, if you think about the clay, this part is not negligible. So then we can think of like a parallel model. So we have electrolyte and we have particle, and there's a surface conduction, or can say surface conduction part when the electric field is applied like this in parallel model. So in parallel model, the mixture conductivity is sum of contribution by the electrolyte and contribution by the particle and contribution by the surface conduction. Here the unit element is, because it's repetitive, you can think that the particles are more here, and there's one more, in upper side also there will be one more particle. Then we can think that from half to other half of the particle is the unit element. So then you have only two clay surfaces. So that's why we multiply 2 here. And the thickness is divided by each thickness is divided by the total thickness of the unit element. And the relative thickness to the total thickness can be expressed with the porosity. So now that the mixture conductivity is electrolyte conductivity times porosity plus the particle conductivity times 1 minus porosity, and the surface conduction times 1 minus porosity, because it's developed by the particle. And here, this 2 over 3 Tp, so particle thickness, can be replaced with this specific surface area. So if the specific surface area is the surface area divided by the mass, that's the definition for the specific surface area of the clay. And then 2 over Tp, which is the 2 over particle thickness, is specific surface area times particle density. So the final equation will be electrolyte conductivity times N. So electrolyte here is the conductivity of the fluid, the pore fluid, and the particle conduction, particle conductivity times 1 minus N, plus surface conduction part. So lambda ddl times surface area, specific surface area times density times 1 minus N. So this is the equation that we derived. And here, then how do we determine the lambda ddl? We can determine from the zeta potential. And this can be also measured using some equipment called the zeta potentiometer. And when the particle conductivity is very low, so that the particle itself is not conductive, like dielectric material, then this part will go to zero, so that the final equation will be like this. This is for clay. Large particles with very small specific surface, then the specific surface area is zero, or almost zero, so that this part will go zero, so that this will be the final equation as applicable to sand and silt. And this is based like a fundamental basis of the Archie's law that we're going to talk about in chapter 12. So then when we plot the mixture conductivity versus the electrolyte conductivity, it's almost like one-to-one relation for sandy soil, like low specific surface area, and the particle conduction is zero almost. No? So then this will be the one-to-one line controlled by the this is the electrolyte only, like n times sigma EL copy related to porosity. Then in general, the sand will follow this kind of Archie's law, and it kind of shows the nonlinear behavior as the ion concentration or electric conductivity of the pore fluid increases. So as it gets more brine or like salty, then it becomes like nonlinear like this. And when it's clay, so this is for the sand, when it's clay, even though the electric conductivity of the electrolyte is very low, almost zero, still because of the surface conduction, by the surface conduction, the initial mixture conductivity is high. So it starts somewhere here, and still it's greater than, higher than the sand. The electric conductivity of the clay, the saturated clay, becomes more dominant by the electrolyte. So with this like straight line, the left side is controlled by the surface conduction, and right side is controlled by the porosity and the electrolyte conductivity. Thank you for listening.